All right, let's dive into one of my favorite topics in all of physics, Lenz's law. You can really think of it as nature's ultimate no free lunch rule. It's the universe's way of saying you just can't get something for nothing, and it is an absolute cornerstone of electromagnetism. Trust me, by the end of this, you'll see exactly why this principle of opposition is so incredibly important.
So let's kick things off with a classic physics mystery. Imagine you take a copper ring and you drop a magnet right through it. Now, you'd expect it to just fall, right? Accelerate due to gravity at 9.8 meters per second squared. But it doesn't. It falls incredibly slowly, almost like it's moving through thick honey. So what's going on? What's causing this invisible braking force? Well, the answer is Lenz's law, and that's exactly what we're going to master today. Here's our game plan. First, we're going to get to the bottom of the core rule behind that reluctant ring mystery. Then, I'm going to show you a foolproof method to predict the direction of the induced current every single time. We'll see how this all links back to the conservation of energy. You know, that no free lunch rule. After that, we'll tackle a really common exam trap involving open circuits, and we'll finish up with a handy toolkit to make sure you've got all this down cold. Let's do it. Okay, so let's start by unpacking the law behind that slow-falling magnet. What exactly is this force of opposition?
Here it is, the official definition. And here's a pro tip for your exams. It is absolutely worth memorizing this word for word. The induced EMF, or current, opposes the change in magnetic flux that produces it. Now that word change, that is the absolute key to everything. We're about to see exactly why. To make this all feel a bit more intuitive, let's use a little analogy. Let's call it the window analogy. Just imagine you're trying to catch rain on your windowsill. If you tilt the window, you change the area that's exposed to the rain, right? So you're changing the rain flux. Now imagine as you try to tilt that window, it starts pushing back. It's literally fighting you, trying to undo what you're doing. That resistance, that fight, that is the core idea of Lenz's law. The change in magnetic flux induces a voltage, an EMF, and that EMF creates a current, which in turn generates its own magnetic field to fight whatever you were doing in the first place.
And listen, this is the #1 spot where people get tripped up. The law doesn't oppose the magnetic flux itself. It couldn't care less how strong the flux is. It only opposes the change in flux. Think of it as an anti-change law. If the flux is increasing, it's going to fight to decrease it. If the flux is decreasing, it's going to fight to increase it. It just hates change. Okay, so we know the current is going to oppose the change. But how do we figure out which way it's actually going to flow? Anti-clockwise, clockwise? Let's build a simple step-by-step protocol to nail this every single time on an exam. Here it is, our 5-step protocol. Let's walk through it. Step 1. Just identify the change. Is the magnetic flux getting stronger or weaker? Step 2. Apply Lenz's opposition. So if the flux is increasing, the new induced field will point in the opposite direction to fight it. If it's decreasing, the new field will point in the same direction to try and boost it. Step 3. Grab your right hand. Point your thumb in the direction of this new induced field. Step 4. Find the current. The way your fingers curl, that's the direction of your induced current. And finally, step 5. What's the physical effect? Is it a push or a pull, repulsion or attraction? Let's put this protocol into action. Look at the left. A north pole is coming towards the ring. The magnetic field lines point down, and as it gets closer, they get stronger, so flux is increasing. Lenz's law says, no way, and creates an upward magnetic field to oppose it. Okay, right hand rule. Thumb up, and look, your fingers curl anti-clockwise. That's your current. Now on the right, the magnet is leaving. The downward flux is getting weaker, it's decreasing. So Lenz's law tries to help it, creating its own downward field to prop it up. Thumb down, your fingers curl clockwise. See how that works? And what's the bottom line here? Notice that in both cases, the induced force always opposes the motion. It pushes an approaching magnet away and pulls a leaving magnet back in. It's nature's ultimate contrarian. It just says no to everything.
So, why? Why does nature behave this way? Why all the opposition? Well, it turns out this isn't some random, arbitrary rule. Lenz's law is a direct, unavoidable consequence of one of the most sacred principles in all of physics, the conservation of energy. In fact, this right here is a classic 3-mark board exam question that you are very, very likely to see. So how do you construct that perfect answer? Here's how you nail it. You start by imagining the opposite. What if the induced current actually helped the magnet instead of opposing it? Well, the magnet would just speed up, all on its own. This would create more current, which would make it speed up even more. You'd have a runaway perpetual motion machine, creating free energy out of thin air, which we all know is impossible. That's why Lenz's law must oppose the motion. It forces you to do mechanical work. You have to physically push the magnet against that opposing force. And where does that energy go? It gets converted from your mechanical work into electrical energy in the ring, which then just dissipates as heat. Energy isn't created, it's just transformed. So it all boils down to this. You cannot get something for nothing. The electrical energy that appears in that ring has to come from somewhere. It comes from the mechanical work you do pushing the magnet. Lenz's law is simply the mechanism that enforces the universe's strict no free lunch policy. All right, now that we've got the core principle down, let's look at a classic exam trap. This one hinges on a really subtle but super important difference, the difference between induced EMF and induced current. Get this right and you'll be way ahead of the game. So take a look at this assertion-reason question. The assertion is a magnet dropped through a ring that has a little cut in it will fall with acceleration g. And the reason is because no current flows. So what do you think? Is this correct? And does the reason actually explain the assertion? Here's how they try to trick you. The common mistake is to think that a cut in the ring just means nothing happens. That is wrong. As the magnet falls, the magnetic flux through the ring is definitely still changing, so an EMS, a voltage, is induced. But, and here is the key, because of that cut, the circuit is open. There's no complete path for the current to flow. And if there's no current, there's no induced magnetic field, and therefore no opposing force. So the magnet just free falls. That means both the assertion and the reason are correct, and the reason perfectly explains the assertion. So here's the golden rule. Write this down, commit it to memory. A changing magnetic flux will induce an EMF, a voltage, in any conductor, whether the circuit is open or closed. But you only get an induced current, which is the thing that creates the opposing force, if you have a complete closed circuit. Whew, we have covered a lot of ground. So to wrap things up, let's consolidate everything into a final, practical toolkit for your revision. Think of this as your error prevention checklist. Let's run through these common mistakes real quick. First, that negative sign in Faraday's law. That sign is Lenz's law. It represents the opposition, so don't ever forget it. Second, be precise with your language. Don't say current opposes the field. Say current opposes the change in flux. Third, remember the difference we just covered. EMF can exist in an open circuit, but current needs a closed loop. And finally, a common misconception is that inductance depends on current. Nope, it's purely about the geometry of the coil. Honestly, this is a great slide to screenshot for your last-minute revision. So if there is one big idea to take away from all of this, it's that Lenz's law isn't just some random rule about directions. It is a profound consequence of the conservation of energy. That opposition exists for a very deep reason. You have to put work in to get energy out. In physics, there is absolutely no such thing as a free lunch. And that's a wrap. You've just mastered one of the most fundamental and powerful concepts in all of electromagnetism. Next time, we're going to put Faraday's law and Lenz's law together to derive motional EMF, which is the core principle that powers every single electric generator on the planet. I'm going to show you 2 different methods to absolutely nail those 5-mark questions. Thanks for joining me, and I'll see you then.